today we are going to be learning about derivatives, not integrals quite yet, but we are going to be learning about derivatives and what they are. So before we can answer the question of what a derivative is, I want to start off with a slightly different question. What is a limit? So the best way to answer that question is by looking at a graph. So this is the standard way to write a limit. And what this says is when we approach, or when x, the input of f of x, approaches a constant, from values greater than a and less than a, what do those corresponding f of x's approach? For x is less than or greater than a. What's the point they agree on? Or more specifically, what's the y-coordinate of the point they are approaching? Not quite agree on. Well, in this case, that's b, right? So it equals b, which is a real number, but b is not always going to even exist. This limit sometimes doesn't exist. So let's say you have a function like this. Not quite. Just a little space from A. There. So from here, we're approaching, let's approach A from both sides. And let's approach it on the f of x's. So for values less than a, those corresponding, for values of x less than a, those corresponding f of x's come to be about here. Make it more functioning. And for values greater than a, we approach this point. Now these aren't the same, right? So therefore the limit cannot exist. And these limits, when we approach from just one side, completely ignoring the other side, called the one-sided limits. So here, because the one-sided limits don't approach the same point, then this two-sided limit doesn't exist. Right. And for your information, b equals 27 and a equals 3. This is a continuous function, right? Just so happens to be f of a. This limit happens to be f of a, which is the y-coordinate. So these are the one-sided limits. The minus is for values less than a, and the plus is for values greater than a. They aren't exponents. In this case, they are equal, and they're equal to b. Since they're equal to b, that means these two are equal, and therefore the two-sided limit also exists. Now, a function doesn't have to be continuous in order to have a limit. It can be discontinuous. So let's say our new function, our new f of x, is discontinuous at this point. So now, as you can see, when we approach here, we seem to be approaching this point that's about b. when we approach here, we also seem to be approaching about b. Draw the arrow better. We seem to be approaching about b, right? Even though it's discontinuous. And this gives another way to define a limit. So a limit turns f of x into g of x, where g of x is continuous at all the points on this limit. It's continuous everywhere. I like to call g of x the fill-in-the-gap function. So now, just evaluate g of x at a, or g of a, and you have your limit. Because what we saw earlier here, so what we saw here was that when we approached here and here, when we approached, they approached one point, and they happened to approach b27, the actual value of the function at that point. So in this case, f of x equals its g of x. So you can think of g of x as being a sort of property of f of x, or the limit of f of x as x approaches a. G of a would be the answer. Now there are a lot of ways to compute limits, and here's a chart listing some of them. So first, we just assume f of x is our g of x, and then just try to substitute in a in the place of x, because usually f of x actually is the g of x, like in the x cubed. So if we substitute it in, a couple of answers we can get. We could get b. That means we're probably done. We can get infinity, which I didn't cover yet, but you get something like this, right? An asymptote. Or you could get does not exist. For even the one-sided limits, I haven't shown you that. Let me pick a more contrasting color, green. So if this point right over here is A, right? One side is the asymptote, the other isn't. And an asymptote actually is sort of a quote-unquote does not exist, but sometimes it's not accepted as it does not exist. Or we can get 0 over 0, the dreaded 0 over 0, and this is called indeterminate form because sometimes you can actually end up with a valid limit that's does not exist, or infinity. So there are a couple of tricks we can use to uncover that real, I guess you could say, limit. The first is just factorizing. So you have something like x square minus 1 over x plus 1, and the limit as x approaches 1. Whoops. How about x plus minus 1? So x plus minus 1 or x minus 1, if you try to assume x squared minus 1 over x minus 1 is the g of x, and substitute in 1, you're going to get 0 over 0. But you probably know that x squared minus 1 is the same as x plus 1 times x minus 1, or x plus minus 1. So you could try canceling, and if you notice, they aren't exactly the same function. This x plus 1 is our g of x, because in f of x, if we try to input 1, we get 0 over 0, but in our new g of x, x plus 1, we get 2 when we input 1. So now this is our new g of x, and when we try substitution, we get 2. We always go back to direct substitution when we use these strategies. Next, you have trigonometric identities. So that's something like, you could say sine of theta over 1 minus cosine of theta, and the limit as x approaches 0. If you know your trigonometry, you know that this is going to end up as 0 over 0 if we assume that this is our f of x. If we assume this is our g of x. But we could use our trigonometric identities to say that since sine of theta squared equals 1 minus cosine of theta squared, okay. And now we can use factorization to get 1 plus cosine of theta. I think you can see why. And this is our g of x. For the same reason that x plus 1 was our g of x in the factorization example. So now if we try substitute in 0 for theta, not x. If theta approaches 0, if we try substitute in theta if we try to substitute in 0 in the place of theta, we get 2 again because cosine of 0 is 1. And next is rationalization, which is basically the same thing as factorization. Well, sometimes. Sometimes it's better than factorization. It really depends on the problem you're trying to solve. But in this example, we could use both. So let's try x minus 1 over the square root of x minus 1. And the limit, the x approaches 1. Well, 1 minus 1 is 0. The square root of 1 is 1. So 1 minus 1 again is 0. We get 0 over 0 if we assume x minus 1 over the square root of x minus 1 is our is our g of x. So we could use rationalization by multiplying the denominator by the conjugate of the denominator and the numerator by the conjugate of the denominator. So basically that looks something like this, just to keep it equal. And now we can change this to an x minus 1, and then up top we have x minus 1 times the square root of x plus 1. To construct our g of x, we will cancel out these. And here we have our g of x, which when we substitute an x, we get 2. And you could have also arrived at this solution by factoring, thinking of x as the square root of x squared to get the square root of x minus 1 times the square root of x plus 1 over the square root of x minus 1. Now if we cancel out this, we get the square root of x plus 1, which was our answer that we got before. We won't discuss L'Hopital's rule quite yet. That's for later. And now that we understand limits, we can move on to derivatives. So, what is a derivative? Well, again, the best way to answer that question is by using a graph. So, a derivative is the rate at which any function is changing. So, if we have a line, the rate at which that line is changing, or the steepness of that line, is going to be m, right? Because this is y equals mx plus b. It's our slope. It's the rate at which the function is changing. Or, since the rate at which the function is changing is the change in the function over the change in the input, delta y over delta x, m equals y sub 1 minus y sub 2 over x sub 1 minus x sub 2, which is basically the same thing as m, and that's the same thing as this, so we have a big triangle, right? But what derivatives do is they don't take a big large delta, which looks like this. Instead, what derivatives do best is they find the slope of a secant line between x and this x plus h. It's an increment. So you could say it's a delta at this scale. So delta x, or commonly said as dx, and then this is dy. I'm writing it inside for lack of space. Let me see if I can make that a bit more legible. Dy. Right? So this side is dy over this side is dy dx. Now the slope is dy by dx, where y is the function. And now this actually outputs another function, because the derivative is a function because it outlines the behavior of all of these slopes. So it's like a function that outputs a whole bunch of m's at that point. And what's special about derivatives that normal slopes don't have is that it's actually, as h approaches 0, so this might be delta x, and actually this would be dx, and this would be dy. And you can see why this works at all the points. There's a function, right? So it's something like this. It's the rate at which that function is changing, and it more closely approaches the tangent line. So if we get rid of this x plus h, this is almost a tangent line, right? So it's something like this. You can barely see it. Dx and dy. It's much smaller in reality. So dx is basically delta x, or x plus h minus x. And then this m at all the points is f of x plus h minus f of x, or the change in f of x, delta f of x, or delta y, right? this turns out to be h, and you could also write h as dx. You could also write this as dy. So as dx or h approaches 0, we get the limit, but this is not our g of x. In fact, let's put that in. So runaway graph. So the limit as h approaches 0 of f of x plus h minus f of x equals df of x with respect to x. Or, the derivative of f of x with respect to x. I'll get to the with respect to part in another bit, but you can ignore that for now. So this is not our g of x, because if you were to substitute in 0 for h, you would get 0 over 0 very obviously. So since this is not a formula, rather a definition, there are a lot of creative ways to come up with all kinds of limit formulas. So let's walk on. And find the derivative of f of x equals x squared. I thought we were gonna do cosine, but looks like this weird dude interrupted, so I guess we'll have to put that on halt for a few seconds, or 1 or 2 minutes. So since x squared is not a transcendental function, or it's used commonly in algebra, x squared. F of x equals x squared is commonly used in algebra, so it's not a transcendental function, and it's not a trig function either. Well, trigs have their identities, but it's a transcendental function, so we can use our formula like a definition. We can use our definition like a formula. I meant it the other way. So here we have the limit as h approaches 0 of x plus h the whole square minus x squared. And obviously you can see where this is going. Now we can cancel out the x squares to get 2xh plus h squared over h. Now let's divide the h's. And this is our new g of x. Because if you haven't noticed, when we substituted the last few times, we didn't really get a defined value for our limit. When we substituted in 0 for h, we didn't get a defined value. Now we do, and when we substitute in 0 in the place of h, we get 2x as the derivative of x squared. And actually, there's something There's something pretty cool about power functions like this. So x to the a, the derivative of x to the a with respect to x equals ax to the a minus 1. And I guess I should do this, but you could put this in parentheses. It's kind of implicit, right? If you've learned the order of operations, it is implicit. Okay. And actually, you can prove this for yourself if you don't want to take my word for it. So try to prove it with x cubed. Or you can try to figure out a geometric proof for x squared, since x squared represents a square with side lengths of x. So I'll wait. Okay, you're back? Great. Now let's try to prove the derivative of cosine that I wanted to do. So let's put cosine of theta in the corner so we know what we're doing. The best way to prove cosine of theta, this time I'm going for a geometric proof, is by using a unit circle and a triangle, because all the trigs are about triangles. I mean, they're called the trigonometric ratios. They measure triangles. So cosine represents this side, the adjacent, at least relative to theta, right? We're doing it relative to theta. And if we nudge that theta, or if we change the value of that theta by a bit, you notice that our new cosine is much shorter than what it was here. And that's kind of strange, don't you think? It says that cosine increases in the x direction. Or, as theta increases, the adjacent side decreases, which, when you think about it, kind of makes sense. Right? And I'm pretty sure it works in the second quadrant too. So, since as we go down, we get shorter angles. If we go up, we get larger angles, right? These are basically like negative angles, in a way. So, we can take a derivative by nudging it, by changing this value of theta by h or d theta. I personally like d theta. And we get a triangle. We can construct a triangle. Right? So this is the hypotenuse d theta. And actually, let me put that. And this is the zoomed in version of that triangle. Right? And I can prove to you why this angle is theta right over here. So, since alpha plus theta equals 90, right? It has to, because 90 plus 90 has to equal 90 plus 90 equals 180, and a property of all triangles is that the sum of their angles must be equal to 180, and we already know one angle, so we can't deduce exactly what those two angles are, but what we do know is that their sum equals 90 because it just has to. 90 plus 90 equals 180, right? So that means if this is, let's just take a tangent line over here that's perpendicular to this hypotenuse, or radius, whichever you like. It's a unit circle. That must mean that this angle has to be theta. That means this angle right over here has to be theta, right? And if this angle is theta, then this angle, if we just sort of add it as well, right? So if this is 90, then this must also be 90, right? And since alpha plus theta equals 90, this must equal theta, this must equal alpha, and this corner angle must equal theta, right? Since if we make a line here, and we draw a line perpendicular, I never drew so much on the screen at once. And if we draw something like this, this has to be equal to 90. So this must be theta. And this must be alpha because this angle is theta, right? And since there is a 90 degree here as well, alpha plus theta is 90. So if this is theta, that must be alpha. And since this is a right triangle, alpha plus 90 equals theta, right? Doesn't that make sense? Because here, theta plus alpha plus 90 theta plus alpha equals 90, right? So theta plus alpha minus 90 equals 0. So if we move alpha to the left, if we move theta to the left, get alpha minus 90 equals negative theta. If we multiply both sides by -1, no, I think I've done something wrong over here. But you get what I mean, right? This has to be theta because this is 90. And this is alpha, right? Makes sense? And what you notice here is that this is the change in cosine of theta, right? Since this is theta, this is its cosine of theta, or it's the change in the cosine of theta, because when we draw a triangle with that new theta, right? Now that cosine has changed definitely in a negative way, so actually the d cosine of theta points in the opposite direction of the positive direction of the x-axis, which is this way. It increases this way, right? And for greater thetas, you get smaller cosines, which is what we proved earlier. And remember, for smaller d thetas, this triangle's hypotenuse is more closely going to approach the actual arc length of this. The actual arc length of the circle. At least between those 2 points. Right? For smaller d thetas. And the derivative of cosine of theta is d cosine of theta over d theta. Now this must equal a negative number because d cosine of theta is negative and d theta is the hypotenuse and d cosine of theta is the opposite side relative to theta. So negative opposite over hypotenuse relative to theta, well, what's that? It's negative sine of theta. That's right. The derivative of cosine of theta with respect to theta is negative sine of theta. Cool, isn't it? Now let's move on to the next one. And this and the next two are actually just rules about derivatives of different functions, I guess you could say. Or different groups of functions. So the derivative of f of g of x with respect to x, what is that? Well, when we do this with respect to x business, what we're really saying is, as x changes, what is the change in this, and what is the ratio, right? So instead, if it was g of x, it would actually be g of x increasing, the entire g of x, not necessarily x. I mean, I guess it has to, but what we're doing is we're calculating the ratio when g of x and only g of x is increasing. We're not using x as a sort of, no, I wouldn't call it an outpost. We're just treating g of x as the input to f of g of x, which it is. So you could also say the derivative of f of g of x, oh yeah, right, with respect to x, right, is, well, I don't want to write it. I'll just put it here. The derivative of f of g of x with respect to x equals the derivative of f of g of x with respect to g of x times the derivative of g of x with respect to x. That makes sense because if you cancel out these, you get the derivative of f of g of x with respect to x, right? So this makes total sense. This is actually called the chain rule. So there's also a multiplication rule and an addition rule, which you feel like discovering, but you don't want to do differences and division, because division is basically something like this. So O over n is the same thing as O times n to the negative first, right? And O minus n is just O plus negative n, right? It's just this. Division is a different version of multiplication, and subtraction is a different version of addition. So you think power functions would be a good place to start finding your quest for factors, sort of. You want to find out the multiplication rule. You think power functions are a good idea because you know what they multiply out to, right? So in this case, this would be x to the fifth. The derivative of x to the fifth with respect to x is 5x to the fourth. But this time, you want to look in between the lines. What you notice is that 5x to the fourth equals 2x to the fourth plus 3x to the fourth, and that, strangely enough, equals 2x times x to the third plus 3x squared times x squared, and even more strange, x cubed and x squared are included here, right? And even stranger, 2x is the derivative of x squared and 3x squared is the derivative of x cubed. So now, see if you can try to figure out the rule for multiplication functions. Well, this is it. The derivative of f of x times g of x with respect to x equals f of x times g prime of x, which is called Lagrange notation. And this thing just means the first derivative. We'll get to second derivatives in a bit. Well, we won't get into second derivatives today. But second derivatives are basically just derivatives of derivatives. So you would write that as this, or you could write it as this. No idea why it's written this exact way, but it is. So f of x, which goes there, times g prime of x, here it's just switched. Here this is the f of x, and this is the g prime of x. And here we have g of x times f prime of x. So here this is f prime of x, and this is g of x. Right? Some people remember as left, d right, right plus right, d left. Left is the f of x, d right is the derivative of g of x plus g of x, or right, left d right, right d left. Right is g of x, and d left is the derivative of the left, or f prime of x. Right? So now, you want to add stuff like this to get an addition rule. And you know that this is simply the derivative of 5x, the derivative of 5x with respect to x. And I haven't, or I guess I have, indirectly, told you that this is 5. Why? Because this corresponds to a line, and the derivative of a line is just its average slope, right? So that's y over x, or delta y over delta x. Here, there's not really much of a change, right? Or, yeah. So this is just y over x, or 5x over x, and that equals 5, right? Or you could think of this as the mx plus b, where b equals 0. So 5 is just the mx, and m is the slope. So we can just cancel out the x, sort of, and get m instead. So now we know the derivative of this function happens to be 5. But again, you want to look in between the lines and find out that 5 equals 2 plus 3. I mean, obvious. But what you see is that 2 is the derivative of 2x, and 3 is the derivative of 3x. Seems fishy. Now pause and see if you can figure out the derivative rule of addition. Okay, you figured it out? Well, it's the derivative of f of x plus g of x with respect to x equals f prime of x plus g prime of x, very obviously, where 2x is f of x, so 2 is f prime of x, and 3x is g of x, so 3 is g prime of x. And I want to end at last with another function, which is the derivative of e to the nx with respect to x. And one thing I really want to tell you, or i.e. that will be very useful for you, is that the derivative of e of x with respect to x equals e of x. It's a really big celebrity for new people, I guess. People knew the derivatives. This is really important. This is really important. Now you might be asking why this is so. Well, it's like asking why 1 happens to be 1, or why 1 times 1 happens, well, to be 1. It's kind of like the definition of 1. 1 of itself is 1, right? So this is sort of a property of E, and there's no actual point in questioning why this is so. It's a property that it has very specifically to itself. So now we can actually use the chain rule here. This is like our first application of the chain rule here. And we can write it as this, right? So the derivative of e to the nx with respect to nx times the derivative of nx with respect to x. Well, we know that this is n, right? But this one is going to take a bit more thinking. So let's just imagine this as our g of x, right? Or, even better, let's just cut out this n for now, right? Let's just assume n of x equals its own x, sort of. So let's cut out the n's, and what do you see? Well, you see a slightly mutilated version of this, right? So this must be, in this case, this is e to the x, but then when we add back the n, it's e to the nx, right? We assume nx is its own x. So we write that as e to the nx. It's a little complicated to explain, but I hope you get it, or I hope I've done it well. So that turns out to be n times e to the nx is the derivative of e to the nx with respect to x. And the derivative of e to the nx is proportional to itself. Isn't that cool? And actually, this gives a quote-unquote justification, more like, of this, because here, n equals 1, and 1 times e to the 1x, well, that's just e to the x, right? So we are done for now, and next we have implicit derivatives, integrals, and antiderivatives, or indefinite integrals. So, bye, I guess.